In this problem, we have this Cartesian product, right, of these two small sets of numbers. And we define another relation, which is this pair is related to this one if and only if the sum of the two numbers divides the sum of these two numbers, right? And we're asked to describe the maximum minimum of A with respect to this relation. All right, so let's see. First of all, we're going to list all the pairs because 3 by 3 is 9, so there's 9 elements in A by A, right? And perhaps it's a good idea to list them all. So with 0, we have 0, 2, we have 0, 5, 0, 8, right? Then we also have 1, 2, we have 1, 5, we have 1, 8, then we also have 2, 2, 2, 5, and 2, 8. These are all pairs that you have here, right? And we're going to need the sums to compare them, so let's calculate the sums. This is 2, this is 5, this is 8, this is 3, this is 6, this is 9, this is 4, this is 7, and this is 10. And as you can see here, all these elements are different. So if we define the set B with all these elements, which are 2, 3, 4, 5, 6, 7, 8, 9, and 10, there is a bijection between all these elements and the elements of B, right? So if you have a pair here, the bijection is just a mapping to the sum of these two elements, right? So this is a bijection. And it's a bijection because, I mean, there is only one. Every one of these pair maps into a different one. So you have two different elements, they map to two different numbers. So it's an injection. They both have the same cardinal, so the number of elements here is the number of elements here. So this is a bijection, right? It's reversible. In other words, if I give you 7, then you know I'm referring to the pair 2, 5 uniquely, right? Okay. So instead of dealing with this set, which might be more complicated, and given that in this set the order relation is just the division relation, right? We are going to use this set B, and then the conclusions that we get from here can be translated into the conclusions for this one, right? Okay, this is called an isomorphism, by the way. This is an isomorphism. We say that the set A times A with the relation R that we have defined is isomorphic to the set B with the relation division, right? And as we have explained for isomorphisms, what this means is that everything that happens here can be translated into something that happens here and the other way around. So that's why we're going to study this simpler set. Okay, what is the Hasse diagram of this? And just to have something visual in order to answer all these questions. Well, what are the minimals of this set? Well, the minimals are the elements that are not divisible by anyone in the set, and these are the prime numbers because 1 is not here. So this is 2, 3, 5, and 7, right? So let's write here 2, 3, 5, and 7, okay? Then once you remove them, you're left with 4, 6, 8, 9, and 10. And what is the next layer of minimals? Well, you have 4, you have 6, 8 is divisible by 4, 9 is not divisible by any of these two, and 10 is not divisible. So you have the next layer, which is 4. You got here 6. Then you got here 9. And here you have 10, right? And finally you have 8, right? 8. Okay, so how are they connected? Well, of course, this is connected to this only. 2 is connected to 6 and to 10. 3 is connected to 6 and to 9. 5 is connected to 10. Okay, and that's it. 7 is not connected to anyone. And here, 4 is connected to 8, and that's it. So this is the Hasse diagram. Well, maybe we could have drawn it in a better way, but in a cleaner way, so to say. So maybe, for instance, we can write here 8, okay, then 4 here, right, then 6 and 9, 6 and 9, right, then we can write the 2 here, okay, the 3 here, that's fine, right, but then the 10 is better to draw it here, and the 5 is also better to draw it here. And then you have the 7 here. Okay, if you do this, then this is related to this, this is related to this, this is related to that, this to this and to this, okay? And then there's also this connection and this connection, and that's it. So this has a diagram and this one are the same, and maybe this one is cleaner because the lines do not cross, okay? So we're going to use this one. Okay, we need to describe the minimals of this set, and these are, well, of course, the bottom layer, right? This is the minimals, because all the other elements are larger than some other element in the set, right? So the minimals are 2, 3, 5, and 7, okay? What are the maximals? Maximals are all those numbers that have none above them, and this is 10. Well, this is 7, of course. 7 doesn't have any other number above it. So also 8. Well, actually 6 too, right? So 6, 7, 8, 9, and 10. None of these elements has anyone above them, right? So this is the list of all the minimals, the maximals. The maximals will be. Okay, notice something, and this is important. 7 is at the same time a minimal and a maximal element. This can happen, right? But when this happens, that means that this element is not connected to anyone. Right, like here, you have an isolated element. An isolated element is always a maximal and a minimal of the set. All right. Now the next question is whether there is a maximum and a minimum. Well, clearly there isn't. Right. There is no element which is larger than any other element in the set. Right. Not even the 8 here, and no element that is smaller than or equal to any other element of the set. So no maximum, and no minimum, right? And let's see what else we need to describe. Okay, that's it, right? This is for B, but of course the question that we're asking is about A, so we just need to translate this. So minimals of A are all the pairs corresponding to those. Let's see, this is, well, 2 is 0, 2, right? So 0, 2 is 1, 0, 2, right? 3 is, I think, is 1, 2, yes. It's 1, 2. Okay. Then 5. 5 is 0, 5. That's right, 0, 5. And 7 is 2, 5. Okay, and the maximals of A are, well, 6 corresponds to 1, 5. 7 corresponds to 2, 5. Then 8 corresponds to 0, 8. 9 is 1, 9. 1 8, sorry, and 10 is 2 8. Okay, so this is the answer of the problem.